So let's get started.
昨天你说到
So here are some few heads up. We will announce our second hands-on today later, and then we will have our midterm next week, and it will be a closed book. So the coverage probably will be until the slide we start today. Okay, so I hope we can finish the whole lecture too, but depends because there still have a patch test content. Not quite sure if we can finish all the patch test. So let's see where we stop today. And then we will have invited license to give us a talk on April 27th. Okay. So last week, actually, we are not. 2 weeks before, we talked about like block IO layer, block device driver, those kind of stuff. And also, we also talk about low structure file system and part of like what is the structure of file system. So let me quickly do a quick recall on the file system part. So for file system, there are 3 main important components. The bottom one is the file system. So usually people will call it like file system instance or like structure, something like that. And it includes a lot of possible file system like ext4, 3 or XFS or even like F2FS, TFS, those kind of different file systems. Even some of them have sharing similar structures. For example, for the ext family, actually they have very similar structures, but actually there are slightly difference from one to one. So there comes the things called virtual file system. So virtual file system can offer a uniform interface for the user process, or you can think about for our programmer. Then we can easily interact with the file system without considering about we are now interacting with exe family, or we are interacting with like XFS, or even interacting with like Windows NTFS, those kind of stuff. You don't really need to consider that much of stuff. What we need to know is we are going to talk to the file system. So the virtual file system will help to be a translator to translate our comment to what file system can understand. And between them, there's a thing called patch hash. So you can think about like when we are going to read out a file from the disk, for example, then if next time we are going to read out the same file, if there is no wait. Sorry, is my voice clear for the online? Okay, like this. All right, so okay, so file system is kind of a group of method and data structure. So this part actually can very explicitly, we can find it in the virtual file system part. Like later this lecture will talk about what is about method and what is about the data structure. Okay, and as you know, without the file system, data will be one large body on store device. So it's just a very continuous like 1 and 0. So it is hard to identify what is like a file. Is it like the media file, or this is a document? So those of the like high level information, they're all because we have file system. So those kind of high level information can be maintained. Okay, so Linux supports many file systems. I just skip it. And there is a good analog between the file systems to the library. I think it will be easier for you guys to understand what is the position of the IO systems. So for the applications and files, you can think about it looks more like library users request books. So library users just like our applications, and the books requested is just like the files. And when the library users is going to get books, before that, we need to check the catalog system. So catalog system is just like in the library, usually there is some computers and there is catalog, so we can know where is the location of the book. And the catalog system is just like our file system. So the file system doesn't really store any like file content stuff. File system is just like to lay out where the file should be put and what is like the relationship to get the file. And then we will have the library staff. So library staff acts like the book, the block layer. So it physically retrieves the book from the correct shelf and slot. So the shelf and slot inside a library, you can think about it just like like each device. So this is a quick analog between the I/O system and the library. Okay. So more technical part for the file systems. Actually, there's two very important concepts. The first is called a file descriptor. Actually, file descriptor is kind of the data structure. It is just like an integer to identify the open file in all file-related operations. And open file is very important. What do I mean for open file is a process used like system code to open a file. So then this file becomes an open file. Otherwise, the file is not open. I mean, just like if you do not open a movie from your disk, then the movie doesn't have the file descriptor. The file descriptor only be assigned when there is one process opening the movie file. Okay, so it is assigned by the kernel when a file is open and is valid only within a process. And different processes that have their own file descriptor. So there is possibility like two processes having the same file descriptor, but it points to different files. It is possible because file descriptor is only within the process, so it is independent between process. Okay, and this is the structure. I mean, this is just a very brief structures between the file descriptor and inode. So another important concept is inode. Inode, it acts like an ID for each file. So the ID you can think about as just like each file should have their ID. No matter the file is open or not, it should get an ID. And the file, what I mean is the file stored on the storage device. So we say this is a file. Okay. And the file can be open or it can be not open, just like it just uh, resides on the storage device. But no matter what is the stat, the file should get an INO number. So the INO number is going to differentiate from file to file. Okay. And then for each process, how can the process use of this file descriptor to get an INO? Because the file descriptor cannot get the real position of the like the address of the file. We need to do a translation between like the file pointer and then the inode. Okay, because only the inode will contain the information of the file address. Okay, and then actually people might come up with one question is why not just use this file descriptor table and the inode table? Why there is a middle one? Why there is a system-wide open file table? Okay, so actually I give you two examples to try to convince you the system-wide open file table is quite important. I will not say this is a necessary design because you can also have the design with only the file descriptor table and the inode table, but the complexity will be super high. I mean, you need to pay a super expensive overhead. Okay. The first example is because in Linux, this is a multi-process system. So we have multiple processes. And if we have process A and process B, they open the same file. But the thing is, they might not do the same operations on the same file. For example, file A and file B, they open the same like document, the Word document, for example. And maybe maybe process A modifies the very beginning of the document, but process B modifies the very tail, close to the tail of the document. So actually, we need to differentiate like these different like access behavior, right? So you can see in the open file table, there's a thing called file offset. So it is going to record which locations this process is going to access. And then it is also possible because process A and process B, they are different processes. So they might have different access mode. For example, it is possible process A can only read or maybe can only write, and maybe process B can have the read, write, or execute. So they can have different access mode. But if we don't have this open file table, then maybe our file descriptor table should be more complex, or maybe our inode table should have more information to capture of this kind of information. Okay, and we have another example. So this example is about a fork. If process A forks B in Linux, which means process B inherits files from process A. So in this example, you can look at file descriptor 2. Actually, both process A and process B, their file descriptor 2 points to the same file, right? So this one, probably it is a kind of the scenario of the inherits. So in this case, if there is no open file table, then here comes a problem. Like if process A or process B, it updates the file, then there will be trigger copy on write, right? So the copy on write will directly conduct on the inode table. And in this case, we need to have more information and more complexity to maintain this inode table. But if we have an open file table, it just works like a translation between the file descriptor and inode. So we don't really need to modify the inode table. We just insert a new entry for the copy on write process. Then the open file table can do a good job in this case. Okay, so this is just two examples just to let you know there are some benefits for using the open file table, but this is not super necessary. I would say it will give you a good efficiency, but it is not like always necessary to have the third table. If you think you can pay off for those overhead, then using the file descriptor table and inode table only is also possible. Okay, so the layout concept of a file system, and this is going to explain how the data or like how a file is stored on the hard disk drive or solid state drives. And this is just a big overview about if there is an example, your directory looks like this. You have like two subdirectory, and then for the first subdirectory, there are two files, and the subdirectory one, there is one file inside, and then for the root, there is file 0. Okay, and what will it look like on the store device? Actually, before storing anything on the store device, there are two very example. There are two very like important stuff. Two blocks. One is called boot block. Another is called super block. And boot block is if this disk is going to use for booting from the power out, then there is a special boot block. But if there is not, then there is no boot block. And then there is a thing called super block. Super block is going to contain a metadata or information for a certain file system. So for a disk, actually, you can have different partition, right? You can do like multiple partitions on the same disk. And different partition, you can mount different file systems on it. So it is possible for the same disk, you have multiple super blocks. Because each super block will only map to a certain file system. Okay, so you can think about like what is the kind of metadata required by each file system. Those kind of parameters will be stored in this super block area. And following on, there is a thing called inode table. Okay, so inode table is just like to store the like inode information. So we need to map the inode number and where is the location for the file. So we need this inode table stuff. Okay, and after that, we'll have the first directory called root directory. And because in Linux, there is no differentiate between the directory or file. So directory is also a kind of file, okay? I will show you later why I said this is also a kind of file. So because we have file 1, right? So file 1's content will be stored in a place called data block, okay? So it's just like a block and it stores like file 1's content. And we also have the directory, but we say directory is also a kind of file. So of course, the directory should also be like this. It is called directory block. The block about what is a directory. A directory is kind of like a tree-like structure. You have a backslash and then maybe your home directory and then backslash and maybe your like something like temp directory. So actually what we are going to store is the file path inode and then the file name. Okay. So in this directory entries, you can see there's a lot of entries. So for the first entry, for example, inode4 probably is maybe from subdirectory 0 to file 1. This is called inode4. Okay. And then inode5, you can see that this is another like file structure or maybe another directory because we say each directory and each file should have should have their own inode. Okay. Oh, sorry. And we will talk about this more later because in the virtual file system, directory entries is super important. It will be a little bit complex later. Okay, so let's move on to a quick example about what is log structure file system look like. And before that, we need to let you know why we need this kind of log structure file system. So in the disk perspective, sequential access is very important, especially for the hard disk drive. And the log structure file system is also like it's proposed in the era when people are using a lot of hard disk drive. Okay, so when we're using hard disk drive, we say we hope the access they're all continuous, right? And what is sequential? Sequential is about writing data in a sequential order, but it is not enough because the disk will take all the time. So even you write into the sequential order, but it is possible if you write it too slow, then the disk is rotated too fast, then the order will not be contiguous on the disk. Okay. So usually we have things called write buffer. The write buffer is going to try to mitigate this kind of time difference issue because we can buffer all the stuff in the DRAM first, and then we can write into the hard disk drive at the same time. So even there is a time delay between like file data or metadata, then the write buffer can breach this kind of stuff. Okay. So the example is if we have the things called like like DJ and DK. So DJ and DK, DJ, there are 4 blocks belonging to DJ, and we have an inode belongs to DJ. Okay, and DK the same things because DK is another file, so we have another inode, and then we will say data is this D part, and the metadata is those inode part. So for the log structure file system, what we are going to, the goal is like this. We are going to run this whole segment on the hard disk drive at the same time. So in this case, if the disk rotates all the time, the next time we are going to read out those kind of information, those kind of data, then we can read out those kind of stuff. And there is no random access. Okay. But the thing is, if we do not have this write buffer, then probably the data and inode usually they will not write at the same time. And then maybe usually inode will write into disk first. Okay. And the data, if it doesn't really write at the same time, then the data and inode will be separate in different location. So they will cause the random access. Okay. So this is the case like why we need a log structure file system. And we say the thing is, but how do we know? Like how do we know where is the location of inode? Because this inode is following with the data, but we don't know where the data is. So we also don't know where is the location of inode. So here comes the structure is called the inode map. So inode map is going to summarize several inode information together. So in this case, imap 0 to j is summarized inode 0 to inode j. So in this case, we can quickly locate inode 0 to inode j with only reading out this imap information. But the problem doesn't be solved thoroughly because we still need to know where is the location of imap, which means we still need a fixed location. Without having a fixed location, we don't know where the imap is. So to have a fixed location, actually the log structure file system will allocate a thing called checkpoint region. The checkpoint region is usually a fixed location, maybe in the very front or maybe in the very end of the hard disk drive. So in this case, each time the structure file system can directly read out the checkpoint region, and the checkpoint region acts just like a summarize across IMAP. So it's just like the structure, like the checkpoint region summarize IMAP, IMAP summarize inode. So inode tells us where is the data, like this kind of tree-based structure. Sorry, I think it's a hierarchical structure. Okay. So this is the quick concept of the log structure file system. And this is only for the like file version. There might be another question is if there is a thing, like, I mean, if the example is directly as that, then what would it look like? So let me give you a true example. Here is a like /home and /test. So in the real life, it is very common. We have this kind of directories. Okay. So /home is a directory. /test is the data. Okay. So first of all, you can see actually this one is about the directory data. Okay. And you can think about this big D and the directory sub is like for home, and DJ is for test, just like this. Okay. So first of all, a directory is just a collection of name and inode number mappings. So a directory like a file has their own inode. So first of all, the inode map can tell us where is the location of our directory. Okay. So in this example, the /home directory is located on A3. And A3 is the inode number because the IMAP is a summary of inode. So IMAP will not tell us where is the real data. You only tell us where is the inode. Okay. So IMAP identify, oh, actually your /home directory is located on A3. Okay. So CPU will then come to A3 and read out the inode information. And inside this inode information, it tells us where is the beginning of the data. Okay, so this B0, I mean the first block is from A2. So A2 is here. So A2 means the file content of the directory I know. Okay, because I know is just about to tell where's the location, and the real data is stored here. Okay, so this A2 is going to tell us the data, the file content starts from the location of A2. So CPU can come to read out this D directory. But if you still remember, the directory, actually, this is the data block. Sorry, this is a directory block. Okay, this directory blocks inside, it contains inode. So the inode tells us, hey, actually, inside this directory, there is a file name called test. Okay, and then inode number is called J, like this. So this inode J and then file name test. So how to get this information? Actually, we only know the file name and inode. We cannot get the content. We should use the inode number to map to a correct file content, the data block part. Okay. So once again, we'll come back to the IMAP and then ask the IMAP, hey, we have another inode number J. So could you tell us like where is the inode location? And then after checking with IMAP, like it will find like IJ. So IJ locates on A1. Then your CPU will come to A1 to check about the content of this inode. So after reading this inode, actually we will find like, hey, actually the data, the real file content is stored on A0. The B of 0 means like the first block. Okay. So A0 is where the test content is. Okay. So CPU will then go to A0 and then to read out the file content, or you can think about the data block. Okay. And the file name is not stored in the data block area. The file name is stored in this directory entry area. Okay. So at this step, we can know the file name. And then inside the DJ, inside the data block, there is no file name. Okay. So here comes another example, is the update. If we now update the test file, for example, if you add some contents inside the file, and because test is now stored on data block J, DJ, So after updating DJ, what we are going to do is to write it to a new position. Okay. And then because the location of DJ changed, it changed from A0 to A5. And then the I node should be also changed because the I node for DJ, which is going to tell us where is the location of the data, right? So the location of data change, so we need to also change the I node. Okay, so the I node J change to like point to the to A6. The location becomes A6, and the block inside the I node J points to A5 now. Okay, and I node change, which means your I node map should also be changed. So your I node map should be changed to here, and then that's it. This is what the change we need to fast if we have the I node map. Okay, so the bottom example is going to tell us if there is no I node map, which means if we only have checkpoint region and I node, we don't want I node map. It is also possible, but in this case, we need to update all the stuff. What do I mean? All the stuff is if we come again look at this top example, we don't really need to update the directory part, right? We only need to update the data part because we only modify the test file. We do not really modify the home directory. Okay, but in the bottom example, actually, if there is no IMAP, then we need to update all of them, including DJ and also the directory. Because if there is no inode map, then we need to store extra information in the directory part, right? We need to store those kind of address inside the directory block. So we can let the directory block tell us where is the data. But the drawback will be if there is an update, then we need to update a lot of stuff. Okay. And the problem is called recursive update problem, which means if your directory is super deep, you have a lot of directory, then you need to update all of them. So the update overhead will be super high. But the good thing is you can get rid of the IMAP. You can save some space. Okay, so it's just about a trade-off. Okay, so I think those are things from 2 weeks ago. So now let's start from the virtual file system. For virtual file system, there is two parts. The first part would be also like the definition part. There is like object and then operation to let you better know what is virtual file system. Okay, and then we'll give you some example about why we need this kind of virtual file system stuff. So the key definition is it enables programs to use standard Unix system codes to work regardless of the file system. So no matter what kind of file system in your on your disk, you can use virtual file system to access them. Okay, and the virtual file system, the VFS and the block IO layer provide the abstractions allow user-based program to issue generic system code. If there is no virtual file system, you need to interact with different file system with different system code. Okay, so this is just a very brief like flow. You are now in the user space, you use the right system code, right? And you will be hooked with the virtual file system. There is a code system right. Okay, so this VFS will be hooked with different file system. So the real implementations of the file system actually is here. Different file system has their own file system sprite method. You are using the ext family or you are using the like SFS or like other file systems. Actually, they have different implementation on their write method, read method, their like make the return method. So there are all different kind of this kind of method. But we can have a VFS to hook to different file system. Depends on what your user is going to interact with. Okay, so actually from the user space, you don't really know what is the implementation details and what kind of parameters it is required for different file system because the VFS do the abstraction. It virtualize all this kind of stuff to that you feel like even you are interact with different file systems, they look the same. They have very similar, also like they have the same like structure, but this is not true. Each file system have their own structure. Okay. And current Linux virtual file system, actually, you can think about it is derived from the ext2. So there is a lot of, there is a lot of properties they are shared between ext2 and virtual file system. And this is because at a date, this is going to develop the virtual file system. At that time, ext2 is the main file system. So they mirror a lot of function from ext2. Okay. Okay. So first of all, there is two things. The one is called VFS objects. Okay, so VFS objects, it works like the data structure. There are four primary object types for VFS. So the first one is superblock, like superblock object. Superblock, you already know, it represents a specific mounted file system. So different file systems have different like information parameters or like different configurations. So they are all represented by the superblock object. Okay, and then the second one is called I know object. So I know object is the same like as you know, like representing a specific file on a disk. You need an I know number, but I know number is way more not enough because you still have some other like data type or like access mode, those kind of stuff you need to maintain. So this I know object is required. And the third one is called the entries object. So it represents a directory entry, which is a single component of a file, of a path, sorry. So this is a little bit not easy to understand because the entry object is not about the directory. It's not about the directory block. It's about the path. So if you are using a Linux, you know, like when you are going to change the directory, if you use cd, then you will follow up with this kind of path, right? And this path is going to redirect us to get a file. Okay, but the thing is, from a Linux perspective, actually, this path, we cannot only use this path to get a file. Because for this path, if there is no I know number, then we cannot know where is the like physical address. So this path, how to translate from this path to the I know object, this is how the entry object is going to do. So for this path, actually, this path will be decomposed into 4 D entries. Why there are 4? Because there is the root directory, right? We always need to start from the root. So the first path is root, and the second is /user, and the third is /user/home, and the final one is /user/home/temp. So we need for this kind of information, then we can get the data. Okay, because for each of the path, we can get an inode and we can link to the next level. Okay, and then we will have the last object is called file object. So file object, just like their own definition, it is for file, and file is for the open file. So file object is for like those open file associated with the process, then we will maintain those kind of configuration stuff. So here comes the caveat. The VFS treats directories as normal files. So there is not a specific directory object. So there is only I know object for those kind of content part and the entry objects for the file path part. But directory, you can decompose the directory into the file path to the directory and then the content for the directory. So you can use the entry objects and the I know object to describe the directory. And the key thing is the entry is not about directory. Okay, so directory is just a kind of file, and this is very important. The entry is for the file path. Okay. So we have objects, but this is not enough because objects just like a data structure. But you know, like for file system, there are also like operations. Okay, so there is another category, it's called operations. So operation objects describe the methods belonging to each primary objects. Okay, so the specific instance of the file system, there are a lot, ext family, xfs, all those kind of stuff. Okay, so we will have super operations, I know operations. the entry operations, file operations. So these operations, you can think about it just like to define the corresponding functions for each like super block, inode block, the entry block, and file. Sorry, super object, inode object, the entry object, and file object. Because you can look back to the super operations, which means methods that kernel can invoke on a specific file systems. So there is a example, it's called sync file system. And if you look at like the inode operations, the inode operation is the same thing, it's just a method that kernel can invoke on a specific file. And there is create and link. So link is that 2 weeks ago we talked about softening and hardening. So this is about the link part. Okay, and then the entry objects, there is a things called directly delete. We are going to delete a path name. Okay. And the last one, I think you'll be more familiar with the file operations, because the file is about the open file. So when we're interacting with the open file, just like come to think about it, if you are writing a C program, you use like fopen to open a file. So the next one, maybe you will use the fread to read out the file. And the fread, the read part, is part of the file operation definition. Okay, so those are all like for read, for example, if for ext family, they have their own implementations. And for XFS, you will have another implementation for read. But today, I'm not going to let you know the details about what is the implementation behind ext4, what is the implementation behind the XFS, because there's too tedious. And usually Linux, the textbook will not give you this detailed stuff. So what I'm going to let you know is the high-level concept behind this kind of operation stuff, just to let you know what kind of functions they are collected within this file object, and what functions they are belonging to this inode operations. Okay, and for the details part, if you are interested in, you can just dive into the Linux source code and to check each kind of file system. They will have their own implementation details. Okay. So first of all, let's look at the super block. So it's designed to store information describing the file system. So it also called the file system control block. Okay. So when the file system is mounted, FS and a file system invokes the allocate dash super. So this is part of the super block operations. It raises super block of the disk and fill in as super block object. So what does this mean? Because when you are like trying to mount a file systems, before that you need to do a things called file system create, right? You need to format the disk and then to do a file system creation stuff. So when you create a file system, at a time the super block is already inside your disk. Okay. But there is a possibility as maybe there is a power off, maybe you directly power off your computer and you power up your computer again. And then at that time, in most cases, your disk will not automatically just do the mount part. The mount usually, if you write in your configure file, then there's there. But if you do not write in the configure file, your disk will not directly mount with any file system. Okay, so when the time you think like you are going to mount the file system on that disk, and you will call like the mount system call or something like that. And at the time you call the mount, then the super block object on your disk will be read into the DRAM. So the CPU will now know actually this disk in this partition is mounted by which file system. Okay, so this sentence is going to tell you this kind of concept. All the stuff for the file system, they should be from the storage device. Okay, they read those kind of storage device information to the memory. So the CPU can keep using this kind of information. And this is very short like example for the super block object. You see there is a lot of different kind of parameters here, and there is their data structure. Okay. Oh, sorry. So I'm not going to go into detail for each of them. I just want to let you know there is a very cool thing is inside the superblock data structure. There is a thing called h-op. So this is a structure for the superblock operation. So using this structure, actually, you can link to the superblock operations. Okay, so using this, you can point to your super operation, and this structure is shared between like superblock inode and file, and then the entries. Each of them, they all have this kind of operation pointer to point to the operations. Okay, so if a file system wants to write to a superblock, then superblocks will link to the superblock operations and then to do the write super, this kind of function. So here comes another data structure. It's called super dash operation. So this is a structure, and this is from here. We just open up this structure information. We just open up all its structure, and it will look like this kind of stuff. So here are different kind of, you can say here are different kind of functions designed for the superblock operations, including allocate inode, destroy inode, dirty inode or not, write inode, drop inode, delete inode, blah, blah. So they are all belonging to this kind of superblock operations, because superblock is, you can think about super controller for the file system. So it control a lot of stuff, including to create the inode, delete the inode. You're going to like delete a file, or you're going to create a new file, like this kind of stuff. So the first two is create and initialize a new inode object. So like allocate inode and destroy just deallocate. Okay. And dirty and write, just like when an inode is dirty, then use this function to do a journal update. So dirty, usually we mean the data is updated in the memory, but it's not synced back to the storage device. So this is called dirty. It is dirty because the stat is mismatching between the memories and the storage. Okay. So delete inode just to delete the given inode from the disk. And then put super is release the given superblock object. So when we call it among, this put super, it looks like the destructor. So if you write C++, you know the destructor is going to do the resource release. So put super is doing the same things. Okay, so I'll just skip those kind of description. So the next one will be the inode object. It represents all the information needed by the kernel to manipulate a file. And this file, regardless of open or not, because it can, sorry, it can be a file on a disk without open. It still has an inode number, so it still has an inode object. So an inode represents metadata of each file on a file system, and an inode object, blah, blah. Okay, so inode operations look like, I skipped the inode object part. I mean, if you are interested, you can check the inode object in like Linux textbook, but we don't have too much time, so I just directly skip the inode object description. I think looking at inode operation, you can image what inode object look like. So here are a couple of things like inode object can offer. So the first one is create. So create is create a new inode associated with the entry objects with the access mode. So usually called by open system call. Okay, so it is going to link like the entry object and then this new inode stuff. Okay, and the second one is lookup. So we said the entry usually is for the file path. So when we are going to search a directory for an inode corresponding to a file name, then we need this kind of lookup stuff. And later I will show you an example how to resolve the file path from the entry level. And if we are going to create a link, like symbolic link, just like the soft link, then here also offer us the function to how to link this kind of stuff. And then there comes the make directory and remove directory. So this is quite similar when you are using the Linux command. Like when you are going to remove the directory, you need this kind of command. And this is doing the very similar stuff. It removes the directory reference by the entry from the directory from the directory part. And this one is just about to remove. So the Linux will not really delete it. It just remove the reference. Okay, so we do not really remove the directory content part. Okay. Rename is very important. Okay, so rename usually you can think about in your Linux when you are going to do the rename. If I remember correctly, there is no rename command, right? So when you are doing the file operations in Linux command line, actually there is no a command called rename. But how to do the rename for the file? So you will use the move command, right? You'll use the move to change your name. And this is super important because rename function inside the inode operation, it's doing the same stuff. We move the file specified by the old entry from the old directory to the directory with the new directory with the new name. So it is quite awkward, hard to understand. So later I will show you a quick example about how to do the rename, okay? So before telling you how to do the rename, we first need to know the entry objects because rename is to change the file path name. So we need to know what is the file path structure looks like. And the entry object is responsible for the file path. And this is the hierarchical nature of the file system is managed by the entry object. So if there is a file path /home/hello/world, here will be decomposed into four entry objects /home/hello/home/hello/world, the four file paths, okay? So the VFS construct the entry objects on the file. Sorry, on the fly. On the fly means like the file system doesn't store, sorry, the virtual file system doesn't store the entry objects on the disk. So all the things, they are created when it is needed. Okay, so this is quite different from like inode because inode, I mean, for the inode object, we can read all the inode from the storage device, right? Because the inode is already in the storage device, so just read out from the storage device. But for the entry object, it is a little bit tricky because there is no corresponding stuff on the disk. So we need to build up the file path on the fly. Okay, later we'll show you how to build. Okay, so the entry object can be in one of the three stats. So the first is called use stat. Use stat is to corresponding to a valid inode and is owned by some like user. Okay, so this is the first stat. Sorry, and the second is unused. So it corresponding to a valid inode but does not belong to any user. We just cache it. Okay. And the third one is negative. So it is not associated with any inode because probably the inode is deleted. Okay. Either the inode was deleted or the path name was never correct. Okay. So the reason we have this kind of negative stat, I mean, used and unused, I think it is quite easy to understand. Like it is used and this is unused. But why we need negative? Because if we still maintain this kind of path name stuff, then we can quickly respond to the open system code. We don't really need to construct a new file path while we running the open system code. So you can think about negative is just for if one day we are going to use this corresponding association again, then we don't really need to reconstruct it. Okay. So both the entry objects and the corresponding inode can be cached for faster directory lookup and file metadata access. Okay, so the entry objects, they are constructed on the fly. And after the construction, usually we will store in the DRAM, but we will not write back to the storage device. Okay, because there is no storage backup here. Okay, so there's only one thing that you know for the entry objects. The entry operations is there's a thing called hash. So the hash is going to create a hash value from the given entry. So the VFS calls this whenever it adds a entry to the hash table. And this is quite cool because with this hash table, the entry can quickly find out where is the corresponding part. Okay, but just an optimization. So let's move on to a very important stuff, the rename. So by Linux, it replaced the old entry with a new one having a new name, right? So this is how Linux philosophy for the rename. Okay, so I think you might have a question. Why not directly modify the name in the D entry? Right. Sorry, I think there's a typo. Why not directly modify the name in the directory entry? Right. Why not just replace by the new name? So I can give you two reasons why not doing this very tricky stuff. Why we try to replace the old D entry with the new one. We do this kind of duplicated stuff. The first one is consistency issue. And the reason is because the name update usually is not atomic. So atomic is, you can think of atomic as maybe when you are updating your name, but in the middle of updating your name, maybe your machine crash, maybe there is a power shortage. So those kind of unpredictable situation will make this rename operations stop at the middle. And this is called not atomic, because if this is an atomic operations, there is only all or nothing. All or nothing means there is only success or failure. There is no middle step. But name update is not this stuff, because name update that involves a lot of like operations there. So it is possible you only finish 40% of the operations, but in most of the file system, there is no rollback for this kind of naming systems. Okay, so enough talking. Let me show you a quick example. You will have more feeling. Here is kind of recent one, like consistent issue, and there are two parts, storage device and memory part. So in the storage device, here are inode table, and in the middle, this is called a directory block, and this is file one's content in data block. So in the directory block, there are directory entries, right? So for the entries, it will have the inode number and then the file name for those files inside this directory. Okay. So in the memory, what is in the memory? In the memory, there are the entry. So the entry is for the file path part. So for example, this file path, this the entry objects not only storing the file path only, it also stores the file name and an inode pointer. So given for the like file one's file name, just like this one, for the first file, actually, we will construct a path for the first file. And then there is a file name also in this entry object and also the inode pointer. Okay, so this inode pointer can tell us where is the inode object. So the file path construction is going to get this inode pointer to point out where is the like inode object here. Okay, because this one here inside of the entry directory entries, it only tells us the number. There is no pointer. With the number, we cannot directly find where is the inode object. Okay, so the file path reconstructing actually is going to find out the true link between the inode object and then the file path. Okay, so for the inode object, actually there are several parameters here, and the most important part is the data pointer. With this data pointer, the CPU can get the data from the storage device. Okay, and this data pointer will connect to like the patch cache. So if you look at this example, there is already data here, so we can directly get it. But if the data is not in the patch cache, then the data pointer will point to the someplace on the disk. So you need to get it from disk. So this one is the roughly structure for the relationship between the entry inode object and directory block. So what happens if we are going to update the file name of the entry? Sorry, for the file one. So if we do the update, then update storage is not atomic. Because we update this part is not enough. We still need to update the file name inside the directory entries, right? But the thing is, if you send the update operation and just like you are using a hard disk drive, and probably you update part of it, but it's not success at all. For example, if there is a power shortage, then your file name for file one will be half stack. So which means maybe there is some inconsistency between your current file name and the prior file name. Okay. Sorry. So we call it the partial result. And this partial result will permanently be stored in this disk. Okay, so no one knows is this a partial result, or actually this is what the user intend to update the name. So there comes an inconsistent, and there will be happen an error. So this is first one, the consistency issue. Okay, so a correct way to handle this inconsistent is when we are going to update the file, the file name for file one, we need to copy a new D entry. And this the new D entry will have containing the new name for file one. Okay. So at the same time, we will also create another dirty entries and replace the whole dirty entries, just like the nothing. Like if there is a power failure, then we will have some chance to roll back to this D entry because we copy one. So it is possible there are two versions. We can choose the older version one. Okay, so we can always roll back to the older version. And if it is completely succeed, then we can just drop the old version. We can just keep the new version. Okay. So after that, the whole dirty entry is successfully replaced, then we will just drop the old D entry object. Okay. So this is the case, the first case. And here comes another case is if the new name is longer and there is no space in the block. So here is our dirty entry. So here comes the INO number and the name, I mean the length of the name and the type, and then what is the exact name it is. So usually this part will align with 4 bytes, usually, or maybe some bytes, but it should be a fixed. And which means the name can only be like maximum 255. So there is then like the then like constraint in Linux is because we are using this very similar structure. Okay. But if our next directory entry is like less kind of stuff, and then because they are close to each other, so if we are going to do the rename, if you directly do the rename in place, then if the length of the new name is longer than the older one, then it will cross the boundary to overlap with the neighbor other like dirty entry. Okay, so in this case, there will be a corruption for the data, right? So a better way is we just copy this kind of information to some other place and to make it fixed, and then we can remove the prior version. So it will be quite like simple. We don't really need to fix about this kind of cross-boundary issue. Okay, so this is the second reason why when we are going to doing a rename, we will replace the old D entry with a new one, having a new name instead of directly update the name in place. Okay. So the next question is how to link the file path with the inode. I mean file path just like a file path, but what is the strategy to link the file path with the inode? I was like pointer. So if a user process requests a file, and this is the path /path/2/file. First, the VFS parse to get /path2 file, these 4 components. And the second step is it resolve the path for each component. Resolve means we are going to use the path name to find out where is the inode. Okay. So we will first check whether the entry of the component is 16 or not. As we say, the entry is for file path, and this is constructing on the fly. Okay, so usually we will preload the root directory into the memory, but after the root directory, for example, if this is the first time the VFS meets the path, then we need to do the path resolving. So if not, we will run vfs.inodes operation.lookup. We search a path inode from disk and create the entry. So we will search, for example, /path, and we will search this kind of stuff inside the disk. So how to search? You can link back to the inode map inode, and then the directly, sorry, I think it's here. The searching is just like this. We will need to find the IMAP and then to find out, where is the inode number for a directory. And then for a directory, after reading out the directory, we can know what is the file name. So if the file name matches, then we can know, okay, so this is the corresponding inode. But if this is not matches, then we will need to find another. So actually, this file path resolving takes a lot of time. Okay. So this is the relationship about how to access the kind of file path and how to do the reconstruction. So we will do the same thing if the to and file. To means /path/to. If /path/to, there is no pre-construction in the memory. If there is no the entry object, then we will need to read it out from the hard disk drive. We need to do the path matching from the hard disk drive, and same as for file. Okay. So because when we get the path, then in the directory of path, we can know there might be two. So in the directory of two, probably there might be file. And the problem is how many files are there under this /path/2. So we need to match it one by one to compare with the file name. Okay. So for example, if you only have one directory and there is no file on the path, and you only have one file under two, then the path resolving will be super fast because we only need to look up one entry each layer. But if under path you have a lot of folders and you have different files, then your system needs to go to one by one to check about what is the corresponding file name. Okay. So more about the entry object. Why there is no the entry object in the following graph, in the following figure. This figure is in the very beginning, we say there is a process, there is a file descriptor table for a process opens a new file, right? And then there is the inode table. Inode table is for those files that are already existing in our system in the hard disk device, they should get an inode. But why there is no the entry object? So the answer is, after a file is opened, the file descriptor can directly access the corresponding inode via the open file table. So actually, we don't really need the entry object. You can think about the entry object is going to quickly find out where is the path and then how to map the path with the inode. So after if the file is already open there, then which means we already do this kind of the entry constructions while at the first time you open the file. Okay, so those kind of informations, they're already maintained in this open file table. So we do not really need the entry object here. Okay. So the entry object is usually used for file path resolving, which means this is our first time to see this file path. So we don't know where is the inode number. We don't know where is the inode pointer. So we will run through this kind of file path resolving. For each table, we will check the directory entries, and then inside the directory entries, we'll check if the file name is matched or not. So this is about the file path resolving and then the entry object. Okay. So next one, the file object. So the file object and file operations, it represents the file opened by a process. And there may have multiple file objects for the same file, but each file has only one inode and one D entry. So the reason for this is because each process has maintaining their own file descriptor for the same file. Okay, so multiple file objects is also for the same. It is possible for the same file. You can think about the file objects is corresponding to the file descriptor. So it's very similar stuff. So like the entry objects, the file object doesn't corresponding to any on-disk data. And the reason is file means the file, the on-disk data is opened by some process. So actually, before that, we don't know which process is going to open. So there is no storage part for the file object. Okay. And file system can implement unique functions for each of those operations. So here are most of the stuff you are familiar with. Like file operations include read write, asynchronous IO read, asynchronous IO write, and the read directory, IO control, those kind of stuff. So those kind of stuff you familiar with is belonging to the file operations, which means the process already opened a file. So you are going to apply the file operation function on it. So let me skip this part. So if we are going to put the file system component all together, so first of all, tag structure is for the process. This one is for Linux only. So each process has their own tag structure. So for this data structure, inside there is an entry called files. So these files, there is a file descriptor table. So for this file descriptor table, we can get the file descriptor. Okay. So if you are interested in the tag structure, you can take the operating system course next semester. But if you already took it, then this is the same stuff. And inside this file descriptor table, there are different file descriptor, right? So for this file descriptor, you will point to the file object. So inside the file objects, there are all this kind of stuff. Okay. So for the entry, it is for the file path. For the inode, it is for getting the data from the device or memory. And then for the mount information, it is for this kind of superblock stuff. And because superblock, actually, there is also like the entry. I mean, superblock, which usually means like there is a root directly there. Okay. So sorry. So I just trying to put. Oh, sorry. This is not me. I mean, someone is just going to put this kind of stuff related to the file system together to let you know there are all this kind of relationship from each to each. Okay. So next one, patch cache. Patch cache is, you can think about patch cache is, you can think about this is orthogonal to the virtual file system and mapping their file systems, because patch cache is an extensions to help to buffer to cache the data in a faster device. So this is the overview of patch cache. This is a disk cache. It minimizes disk I/O by storing data in the main memory. Okay, like this. So for the read operations, when the process run the read operation, because this is a system code, so CPU will trap into the kernel space and then to run this check patch cache. Okay, so check patch cache, first of all, there is a thing called read patch, and then CPU will read from the patch cache, and if this is hit, then the CPU will return the result. Okay, but if this is a miss, which means the data is not in the patch cache, then we need to populate from the storage device. So we need to get the data from the storage device. Okay, and the same things, there is a thing called eviction. So which means if the memory doesn't have enough space to maintain the patch cache data, we need to move some data from patch cache back to the storage device, and this is called eviction. So this is quite similar with the CPU cache. Okay, for the eviction, usually people are using this AORU-like solution. Okay, and AORU design, the least recent use design, actually the overhead is quite high. So even in Linux implementations, it is not using the true AORU. People all call them AORU-like. So actually, Linux is using the things called two-list structure. Okay. And the prior one is read. So we have another one is write. Write operation is a little bit complicated compared with read. So the same things in the CPU, like if the CPU received the write system call, and then you will trap into the kernel to first run the check cache, and then the first one is to write patch. Okay, so there are two different ways to write a patch. The first one is called write do. So write do is automatically update both the in-memory cache and the on-disk file at the same time. So this is write do. We write to patch cache and update immediately to the store device. Okay, so in this case, the step can be consistent between the memory and storage. And this is the benefit, just like to match the patch cache and storage to make it coherent. And a write back is to backing storage is not immediate update. So write back is we only write back to the memory. And then we do not immediately, recently write to the store device. We will update to the store device some days later, or like some time later. Okay. And those patches, they will be marked as dirty. So dirty means the step between the memory and storage is mismatching. So data will periodically sync back to the store device, okay? But it's not at the time the data is right into the memory, okay? And the benefit is quite intuitive because data can be coalesced and write back in a batch. So it is possible to act more like the low structure file system. You can think about it like this, okay? So they can collect the data and then do some like scheduling stuff, okay? This is the whole picture of the patch cache. So patch cache usually interact with the virtual file system. So this one is like virtual file system, and then usually, traditionally there's a thing called buffer cache, but buffer cache is not used now. After Linux kernel 2.4, there is no buffer cache using. So buffer cache is usually for the cache for a disk, okay? But now you just need to know they are merged together, okay? So this is the patch cache management in Linux. So there are three important stuff. The first is about the address space. So the address space you can think about is a data structure to help us to identify where is the data inside the memory, because we store data in the memory, but we need to know where is the data. So the addressing, this is called address space. And the data structure for helping to find out where is the data in the memory is using the registry structure. Okay, so I think this is the only thing you need to know for this figure. For patch cache management, the key thing is about the address space. Address space is a quite complex data structure inside Linux because it also, you can think about when we are going to store the data in the memory, then we need this kind of address space structure. So address space is quite complex. Okay, so there are several stuff. The first is about like the inode, the owner of this patch cache. So usually it's an inode, okay. And then the registry root is the cached patch, okay. And then the number of patches, total number of patches related to the file, because your file size is not a static number. I mean, some file is big, some file is small. So you only use the same data structure called address space. So we need to keep track of what is the size of the number patch. Okay, so as the file size is not fixed, so some file is super large. So we need this kind of address space structure. We need this extra data structure to maintain about what is the mapping between the patch and the file. Okay, as you know, the patch size is fixed, it's 4 kilobyte. But in most cases, your file is not 4 kilobyte. I mean, you have like 4 megabyte, 4 gigabyte, or even 2 gigabyte of the file. So we need to have some link between this patching and then the file. So address space is sit in the intersection between the patch and the file. Okay. So this is the functions related to this patch cache work, the address space operation. So this concept is quite similar to the virtual file system. I mean, dash operations. Okay, so it points out to the operation address space will need it. And this is the address space operation, there are several functions supported by the address space. So write patch, read patch, sync patch, write patches, those kind of stuff. Okay. And for the address space, it maintains the link between the inode, the cache patches, and the device. So here are also some parameters, or like we said, the entries. It describes the information of backend storage device. So like the read ahead information. If you still remember, read ahead means we will read more than like one block from the storage device. Not only the block we require, but we also like do some like prefetch stuff. We will read a couple of them to the memory. So if there is a locator key, like spatial locator key, then we can get it in the memory. Okay. So I just zoom into this backing device information. Backing device, which means it's our storage device. Okay. Just like the storage device back for those kind of patch cache. And the first one is the read ahead, how many patches, the number of patches we are going to do the read ahead. And then the capabilities means whether patches can be written back to storage device. Okay. One more thing. Actually, in your midterm, I will not ask you about this terminology explanation. I will not ask you about what is the capabilities means. This is too tedious. So for the whole file system like slice, most of those kind of things, you don't really need to go into details to understand what each entry is about. I mean, those will not be in your midterm. Okay, that's too tedious for this part. Okay. So how to check if a patch is in patch cache or not? Okay. So we are using this kind of function, the find get patch function, and you can also find this function in the Linux kernel source code. It is under the memory mapping, the file map part. Okay. So this is a patch cache descriptor. So this is a data structure for the cache patch called mapping, and this mapping is using the address space structure. So this mapping is the same as using this structure. So each file, if it is going to cache in the patch cache, it will be allocated this one address space. Okay. Sorry. Okay. So inside of this function, actually there is a thing called patch descriptor, because for the patch cache, the granularity is in the patch granularity. So we need to map into the patch. Okay. So there are patch, and then we are going to do the lookup. And we say this address space, it is using the radix tree to do the lookup. So what we are going to do is, here is the radix tree root, and then the patch offset. Okay. So how to do the lookup? How to know whether the data is in the patch cache or not? First of all, we have the root, as you remember here. This one is our root for this registry lookup. And then we are going to find the offset. So the problem is how to find the offset by giving the root. So the registry look like this kind of a structure. It is aligned with the address, I would say like. So here is MSB and here is LSB. So it splits the address into a couple of pieces. Okay. And then at the bottom, there is a patch address. So from the first slot of the root, then if we link to the left-hand side and the left-hand side, so the two left-hand side means they're all 0. So if we start from the first slot of the root, and then we also choose for the left-hand side, and then for the second slot, then you can see it becomes like 4-0. Only the last one is 1. So this is the radix tree structure. So we just need to check about the address between this each, I would say like leaf slot, and then the required patch address. Okay. Okay, and those are all patch address. Okay, and the thing is, this is conceptually correct, but each pointer at the left points to the patch descriptor. It is not really point to the patch, because this one it only points to the descriptor part. Okay, so patch descriptor is the data structures maintaining all the things we need to get the patch. So not only the address, but also the state of the patch, and then if this is dirty patch or not. So this is linked to the patch related structure. Okay. So actually, this is what it actually look like. So each leaf, it is a patch descriptor. So this patch descriptor can link to the real data, where is the real patch it is. Or you can just check about the stat of the each patch. Okay, so this is how the address space used for the patch cache. So the last few slides. So let me put all those kind of stuff together. So at the very top, we will have a process. Well, we'll get a file descriptor while it opens a file, just like no matter in what structures, if this is the first time for this process to open the file, then your kernel will assign a file descriptor. And then how to check like each file is described by an inode. Then one file, it is possible for n patches in a patch cache, right? Because we say the file size will be smaller or even will be larger than the patch. So it is possible n patches belonging to the patch cache. And how to check where is the patch? We can use the address space data structure, which means we will use a radix tree to check. And the radix tree structure is per file will have its own structure. So you can think about if you have 10 files, then there are 10 address space, which means there are 10 radix tree. Each file will get their own radix tree. Okay. So here, like this is only for one file. Then if you have another file, then you will have another radix tree. Okay. So this is for patch cache. And then after getting the patch, each patch is described by a patch descriptor. This is quite important because like here, actually we are not getting the content or like the true address. What we are going to get from the leaf is the patch descriptor. With this patch descriptor, we can get more information from the patch. Okay. Actually, this part, the patch descriptor part, we have already talked about it in the operating system, but not in this class. Yeah, so just kind of concept here. Each patch is described by a page descriptor, and it can link to a buffer descriptor by the private. So which means like for this information, we can link to the where is the location on the storage device. Okay, so how to read it? Each buffer is described by a buffer descriptor. Okay, so we can, at this point, we will use the block IO to read out the data to require the data from the storage device. Okay, so then all the things related to the file system, the block layer, they chain together at this stuff. Okay. So this is how to read out the file. So the last question is, if there's no room for the patch cache, because if you put more data in the patch cache, one day we will use up all the memory allocated for the patch cache, right? First of all, we need to talk about what is ARU. So ARU assume recent asset patches would be reused recently. So who to re-evict? Of course, is those least recently used patch. Okay. So here comes an example. If this is a list and then patch 4 getting access. So because patch 4 is access, which means patch 4 is a recently access patch. So patch 4 will be moved to the head. Okay. So for the hot code, the left-hand side, like closer to the head is hot and closer to the tail is cold. And P3 does not access for a long time, so we will evict patch 3. So patch 3 is the least recently used, right? So according to our definition. But here comes several use issues. The first one is there is only use one failure. If patch 4 will only be accessed one time. So which means if patch 4 across the whole lifetime, we only access patch 4 one time. Then now patch 4 is super hot, but patch 4 will not be accessed in the future. So actually we should kick out patch 4 at this moment, but patch 4 is now being the most recently accessed patch, so it will never be kicked out at this moment. This is called only use once failure. And there is a second issue is the expensive overhead for adjusting the ORU every time when a patch is accessed. Okay, so what do I mean? So if every time we need to adjust this list, then you can think about when CPU access one patch, right? CPU needs to come to adjust this patch. So CPU needs to like touch the DRAM just only for maintaining this kind of data structure. And it will cause a lot of overhead here. So what Linux is going to solve this two issue, it introduced their two-list strategy. I mean, the concept behind this two-list strategy is very similar to ARU, but it tried to take over these two issues. So there are two lists in this Linux pseudo ARU system: the active list and inactive list. So active list, which means those patches just visit, they will be put into the active list. Inactive list means patches not accessed for a long time. Okay. And the reference means CPU touched the patch, which means the reference. Okay. And here is refill inactive zone stuff, and then the clean, which means if we are going to kick out the data from active list to someplace, then it will be the inactive list. So the path will be if the access is in the active list, then you will always stay in the active list. Okay. But if the data is in the inactive list, then it is touched the first time, it will be moved to the active list. Okay. And then if we are going to kick out someone from the active list, we should kick from the tail, and you will becomes the head of the inactive list. So you can think about this is a little bit like the two chance solutions. So even you kick out the hottest one from the active list, it will stay in the head of the inactive list, so it will not be kick out immediately. So why this is called pseudo? Pseudo is because patches are checked. This is called a reference, and which means this is not periodically, because each patch has a 1-bit access bit in the patch table, and CPU sets the access bit. What do I mean? If you still remember in the patching paragraph, in the patching part, like there is a patch table entries for each patch, right? So inside the patch table entries, actually there are a lot of bits, and one of the bit called access bit. Access bit means the patch is accessed or not. Okay, so this one will be set up by CPU when CPU touch the patch, but CPU will only set up the access bit when the CPU touch it. Okay, but you can think about for the patch, there are thousands of patches there. So there are thousands of this kind of access bits. So if each time CPU set out a bit, then we do the synchronization, then overhead will be super high. So in Linux system now, the access bit synchronization will be run. Usually, is if I remember correctly, is in the like millisecond level. Like couple of milliseconds, CPU will once again check out all the access bit to see if which one is access, which one is not access. So this is the reason it called pseudo, because it is not super recent. Come to think about, in the LRU scenario, when CPU touch one patch full, like we will directly maintain this list. But in the pseudo LRU scenario, CPU will reorganize this position for these two lists. You can think about like every millisecond. Okay, this is not recently, because for 1 millisecond, it is possible like 500 or maybe 700 of pages, they are already being marked as access. So this is not super recently for reacting about the access, but it can largely decrease the overhead. CPU doesn't really need to be super busy just only for maintaining the LRU. Okay. So CPU will periodically check few microseconds to milliseconds for the patch table and then to adjust the LRU list. It will not immediately move the LRU list once one patch is accessed. Okay, so the last one is the flushes threads. So the flusher threads is the 30 patches need to be written back to this eventually, right? So when free memory strings below a specific threshold, this is the first scenario. We are going to flush the 30 patch. The second one is when 30 data grows older than a specific threshold, then the flusher will try to move this 30 patches back to the disk. Or the third one is if a process directly run the sync or fsync system call, then you will force the Linux to flush the dirty data from memory to the storage device. So here are just three scenarios when will the data be written back to the disk from the memory. Okay, I think this is not quite important for the flusher threads. Let me just skip this description. This is the Linux IO stack. Sorry, here is a duplicate. So this one is, if you type Linux IO stack on the web, actually you will see this kind of stuff. And I'm just going to let you know, actually you already go through all this step. So at the very top, there is application. So application is using the system code to interact with the whole system. And the first one will be the virtual file system, because the system code will directly hook with the file systems. Will directly hook with the virtual file system. In this case, your system code can be quite clean, doesn't really need to be so complex. The user only need to know I'm going to talk to your ext family, but I don't want to let my comment to be aligned with the ext. And the VFS will help to be a translator. It can translate to all different kind of file systems. So if you look into this VFS, actually there are a lot of file system implementation there. There are ext family, there are XFS, BetaFS, those kind of stuff. Okay. And then there is a thing called patch hashes here. So patch hash it is going to help us to quickly find out the data in the memory, if there is. And if there is no, then the second step is to go to the block layer. So the block layer, if you still remember, like last one. So this is the patch descriptor after the address space in the patch cache, it will redirect us to get the data from the storage device. So this is about using the block layer, you can get the data from the storage device. And this is here. With this block IO layer, then with the IO scheduler, we will directly get the data from the device part. And here are all different kind of device that is controlled under the block IO layer. Okay, so I think we'll stop here. This is what will be included in the midterm. And then I think we can have our TA to take over for our hands-on description part. OK，等我一下哦，我把它收起来，下面好。好，第二个页吧。好，可以。我
开始。Okay. Hello everyone. I am the TA for this class course. So today I'm going to introduce the assignment to the Valgrind and the PyTorch profilers. And in these assignments, you will see the server's tool and analyze the program and the models. So today I want to focus on two things. And first, I will briefly explain what each tool does. And second, I will go through the requirement of each part. So in this assignment includes 5 parts. So the first one is the main check. The two is the cache grant and massive and co-grant and the PyTorch profilers. And those two are used for different kind of the analysis. So the key is to understand what each tool does and reading the results. Okay. And see the environment setup. And please make sure the old tool is the install. According to the markdown file, you should run the following command on your machines, and Linux is strongly recommend and And the test environment is the Ubuntu 2020. So desktop. And if your environment is not ready, so later the parts will be much harder. So this is the final comment. So let's talk about what is the Valgrind and Valgrind overview. So Valgrind is the dynamic analysis, the framework. So it's giving you different tool to reading different kind of the program analysis. So in this assignments, the Valgrind tool are ManCheck and CacheGrind and Massive and CodeGraph. The ManCheck is detect the memory-related error and the leaks. The CacheGrind is report the cache behavior and the SS-related status. So Massive is the providing heap memory usage over the times. So CodeGrind is the providing function levels, cost, and correlation. So each focus on different things. So let's talk about the first tool is the ManCheck. Okay. The ManCheck is used to detect memory-related errors. So for example, it can be reported invalid memory access and memory leaks. So in this part, you will need to read in the log file and carefully understand the reported errors. So according to the list assignments, you need to run the following command like this. So if your permission is denied, so you can use the change mode 777 in your file name and then requirement is you will need to find the errors from the logs file and annotate the log and explain the error in the report. And there's 6 major different errors that should be identified. So the second part is the CodeGraph. CacheGrind. A CacheGrind is used to analyze cache-related behavior. It shows information about memory access and cache stimulations. So this is the part. The main thing is to comparison the output and see where Stephen is. The spec is giving you 2 executable files. It's a good and one as a bad one. So you need to follow those commands. If your output is limited, you may add the cache simulator yes, this one. So the requirement is you need to take the screenshot of the 2 logs and point out where's the difference and explain why it happens. So for the 2 parts, the main thing is a comparison to log file and carefully and explaining the difference. Okay. Okay, this one next tool is Massive. Massive is the heap memory profilers. It shows how memory heap usage changes during the time programming executions. So in the parts, you should pay attention the memory usage over the time and the peak usage. So first, you need to compare the heap, and we will provide a file. So then, running a following command, and you need to observe the relationship between the time and the memory allocations, and provide a screenshot and carefully and show the total number of the snapshots. Then you need to point out the allocated byte and use the byte of the peak. And next tool is the CodeGraph. The CodeGraph is the used to functional labeling profilings. It records the function codes and function calling the relations. So for this part, you would also use the CacheGrind and to reading the result in the GUI form. So in the GUI form, you need to pay attention in the 4 parts is function cost and code count, and calling and chorus and the code graph. So in this the requirements, you need to answer the 2 questions. First one is which functional is most expensive in the term of the times, execution the time of the calling functions. And the second is which function is the calls the most frequency. So who is the caller? So you need to include a screenshot of the code graph. And the final tool is the PyTorch profilers. The PyTorch profiler is used to analyze the model execution in the PyTorch. And in these assignments, we provide the model is the transformer models. So only CPU allowed, in this part is no cooldown. So for this, the first part, you need to following the tutorial and provide a screenshot of the providing results and identify the top 3 functional in CPU time, excluding the core times, and expand the model labels. And for the second part, you need to output the result to the JSON files and analyze the Chrome trace viewers, provide a screenshot, and point out which 2 functions or colors appear the most in the turn of the times, except for model label. So about the submission form is you need to submit the report PDF and requirement the log file. The file and the file name and the zip structure must follow the spec exactly. So the spec also onto incorrect format will cause the 20% deduction. So please double check your file name and the file structure before you submit. And so overall, the assignment is about learning how to use the different profiling tool currently. So if you understand what each tool does and how to read and output, it will be much easier to finish these homeworks. So if you have any questions about this assignment, so please feel free to contact the TA via email or discussing them on the discussion folder. So thank you.
So any questions for second hands up? There's no, then let's go with this. Thank you guys.
感谢，还有点小紧张。
没事。
是吗？哦，那是5月4号，就是3个礼拜，然后的礼拜1。对对对，我会改一下那个，然后我到时候会上传到上面。谢谢。报告的话，是可以用中文写的，但是好像还是用英文。对，可以用中文写没关系，我不会扣分或什么都可以，但主要是你的表达清楚最重要。那我还是希望就是这样子。好，对。大部分都应该是都其实有第二地方。
Oh, you're here. Yes. It's like the project. Yes. Oh, yeah. They're open for some like for them. But so you're having a program. Yes. Yes. So I think you can send me one. We should like it's a quick call. So introduce process for you. Okay, like that. Yeah. So I know you're interesting. Yeah, check your website, website, and things. And just look at this. So very interesting. Okay. So just send me an yeah. And we can talk about how to push it further kind of what maybe like explaining about what it was yeah. Oh.
哦。哦，对啊对啊。
第一个是想请问说，像这个它就是变成 invalid 的之后，那个变成 invalid 的这个资讯是会写在哪里？是那个 housekeeping？
没错，会在 housekeeping 一里面。
所以它是只会写在这边吗？还是说就是可能有什么可以集中管理的地方会就是让
集中管理的地方吗？通常 page table 也会写，对，就是这里， 通常这里也会写，就是当然是这个话比较简陋啊，就是他通常这边如果要写的话，也可以去标注说谁是。可是等一下，我想一下，哦，我觉得可能不会，因为毕竟它这个是 physical 的 invalid，然后这边它只有去写 logical 对 physical 的对应关系，所以等于是说这张表里面理论上你看不到这个实体位置了，因为它也没更新到别的地方去了，所以它这个记录也更新了。所以除非它做一些很特殊的设计，不然理论上它只有这边会有。因为说实在的，invalid 的资讯在做位置转换的时候是不会需要的。它只有在做就是 garbage collection 垃圾回收的时候才会需要。那因为 garbage collection 你会有很多时间做，就是你会把一个 block 直接读出来，然后知道谁是 invalid 谁 valid，所以其实到那时候再读其实就足够了。
所以他是就是他想要去做 garbage collection 的时候，他才去读，就说哦，可能这个 bug，然后再一个一个看他的 housekeeping 的 info。
对，当然你会说，就是研究导向的话，会有一种可能性，就是你要怎么知道这个 block 里面有多少 invalid 的资讯这样子？那这个状况的话，就是我们可能通常会在维护一个 block 层级的 table，然后会去记录说里面有多少 invalid 的 page 这样子，但它可能就是一个 counter 在那边去做记录。对，但这个就比较偏，就是为了 garbage collection 特别去设计一个资料结构出来这样子。对对对。
可能就是一般的这种状况，不是研究型的话，它就是
就是它就
在
对
里面去。
对对对对对对对。对
另外一个，这个就是这个 hardcore simulation，它的那个 counter base 跟 list base 的部分，就是 counter base 它算说就是它就是它被那个 access 的数量，这样的话会不会就是有可能有个 page 它就是以前可能被 access 很多次，但是它后来就都没有在用，但是它的 counter 比其他的很大，这样。
没错，这就是 counter base 一个很大的问题，就是它有一个很关键问题是，counter 通常只会往上涨而已，然后它就是涨得很高，不代表它是最近被存取，所以涨得很高，它有可能是一开始就被存取，所以 counter base 通常它会有问题是怎么做 reset。counter 有两个可能性，一种就是你 counter 不够用了，因为你 counter 是要理论上这个 counter 可能会吃空间，因为你一 counter 可能就是用 integer 的话，可能就是4 byte 或者是几 byte 这样子。那但是4 byte可以表示其实就是32次方这样子，232次方。但你总有一天，假设你都是不 reset，它总有一天还是会比这个还要来得多。那第二个问题是你说的，就是它随着时间推进的时候，counter 基本上是不会往下掉的。所以 reset 的概念就是说，到底什么时候应该要把它做调整，然后怎么做调整？对，counter base 的设计一直是一个蛮开放的问题，就是无论是研究还是实际上在做的时候，基本上 counter base 相对来讲它的挑战都会比较多一点点。对对对对。
所以现在可能是 list base 的比较多。
我的理解 list base 是比较好用，就像是后面的 Linux 它用的是 sudo list base，因为它就是两个 list 这样子。对，因为 list base 有很大的优势，就是它的 list 基本上是取决于 list 的大小的，但 list 的大小其实是通常是取决于你系统多少资源，所以它总有一天它会没有就用光，用光就是它很好做 reset 的机会，所以它的触发点很好被触发。那 counter base 就没有，counter base 就是都要自己去思考触发点在什么时候。对对对对，
谢谢老师。
谢谢谢谢。
那老师，我想请问一下，就是如果来实体上课，
嗯
就是就是问问题的分数那个的话是
你就是你今天问了什么？对对
下
对，
课也可以，
没错。
上课举手。
不用不用不用，你现在问的都算。
谢谢。
对对对。